Welcome to our discussion on atmospheric dynamics. And we are still working our way through balanced flow. And this is the second PowerPoint video on gradient wind. So where we left off was we had an equation for gradient wind that had three terms. One was the centrifugal force, the other one was Coriolis, and then also pressure gradient. So looking at this, you can see pressure changes in the n direction. This is on a constant altitude chart in natural coordinates. Can you see the n? That's where you have natural coordinates. So we can take this equation and rearrange it so that we have 0 on the other side, and also kind of isolate or separate the velocity terms, the v terms. And when you do that, it looks like you have a quadratic equation. You've got a polynomial of the second degree, v squared. You got v in there also. So this looks a lot like a polynomial. And the polynomial, of course, as I said, is second degree, so it's x squared. And we have an equation that can solve this polynomial. It's called the quadratic formula. And you probably remember that, you probably have nightmares from high school from the quadratic formula. But we're going to use that to solve this equation. And when we do, we're going to assign the 1 over r to be the a, the f to be the b term, and then c is going to be the 1 over rho dp dn. And putting that into the equation, you get terms that look like this. It solves for v, and you have v is equal to everything on the right side. And notice that you have a plus and a minus in this equation. We're going to talk about that here in a little bit, but let me just note that the upper equation is for a constant altitude chart because you've got a pressure gradient. The lower one, we made the change to put it in terms of a height gradient, which is what you'd find on constant pressure charts. So when do you use that plus and when do you use the minus, the plus or minus? Plus in the northern hemisphere and minus in the southern hemisphere. Also, remember that the radius r can be positive or negative. And you probably remember how to determine if it's positive or negative. Draw your s and n coordinates. If n points to the center, then it's positive. And if n points to the outside, then it's negative. So what we're going to do now is compare this to the geostrophic wind. The geostrophic wind assumes that there is no acceleration. Gradient wind assumes that there's acceleration as a result of the curvature of the flow, and that acceleration we call centrifugal acceleration. So let's do a balance of forces. We looked at the balance of forces for the geostrophic wind, and it was only Coriolis and pressure gradient. Now we've got a new force or acceleration, and that's centrifugal acceleration. So when you're going around a low pressure system, of course centrifugal force always acts to the outside, Coriolis acts to the right of the wind, and pressure gradient is trying to pull the air in towards the low. So a balance develops where the wind is flowing parallel to the contours, but you've got Coriolis and centrifugal adding up to equal pressure gradient. A pressure gradient force is strictly a result of the gradient. And if you have a certain gradient, you have a certain pressure gradient force. However, Coriolis force is directly proportional to the strength of the wind. Remember, Coriolis was F times V. So with Coriolis, Coriolis and centrifugal will balance the pressure gradient force. That means that Coriolis is going to be less than what it was for the geostrophic wind, because with geostrophic wind, pressure gradient was balanced exactly by Coriolis. Now Coriolis is less because centrifugal is helping to balance against the pressure gradient. So if Coriolis is less, what would make Coriolis less? And it's not so much the latitude, you're at the same latitude, it's the strength of the wind. So in this case, going around a low pressure system, the wind will be weaker than geostrophic because of the additional centrifugal force. Around a ridge, the opposite happens, where centrifugal force is acting to the outside, but also pressure gradient is acting to the outside. Remember, pressure gradient force points towards lower values, lower heights or lower pressure. So it's like having a super pressure gradient. You're adding the pressure gradient plus the centrifugal force, which means that Coriolis has to balance both. And to do that, the wind has to be moving faster because Coriolis is a function of course, the Coriolis parameter and the strength of the wind. So the wind has to go faster around a ridge or around highs. And we say that the wind is faster than the geostrophic wind, or it's super geostrophic. So the gradient wind is super geostrophic around ridges, meaning it's moving faster than the geostrophic wind, and it's subgeostrophic around troughs. So in summary, the gradient wind assumes, of course, that it's frictionless. There is acceleration, and that acceleration is from the change in direction. We call that acceleration centrifugal acceleration. And the gradient wind is really good for estimating the strength of the wind around lows and high pressure systems where there's significant curvature. So with the gradient wind blows parallel to the contours or isobars, lower pressure to the left in the northern hemisphere, and as I mentioned, it's a very good approximation to highly curved wind. So that concludes our gradient wind discussion. We're going to work into a couple other balanced flows in the next videos.